Hi everyone, welcome to your first nuclear physics lecture of this summer school. My name is Amy Nicholson, and today I thought I would start with just kind of a brief motivation like we would always have in a talk. You want to know why you're sitting here listening to what I'm saying. And I'm going to spend a lot of time talking about the two nucleon interaction. So that's the proton-proton, neutron-neutron, and neutron-proton interactions. And you might ask, why do we need lattice? Why do we care? Why is this important? In particular, when we have experimental data that we can use to kind of extract this information. So I'm going to start off with just a few examples of so-called fine-tuning in nuclear physics. And what I mean by that is that the binding energies of certain nuclei are finely tuned such that they can give rise to, for example, carbon, which we need for life on Earth. So clearly it's very important to understand this. And experiment could tell us what the interaction is, but it can't tell us how the theory of QCD gave rise to the particular fine-tuning that we see in nuclear physics. So the first example that I'm going to talk about is so-called stellar fusion. So this is how small nuclei are fused together in order to power our sun and also to create larger nuclei. So in stars like our sun, they are composed largely of hydrogen gas. So we have a lot of protons running around. It's very, very hot. And because it's hot, the two protons can overcome the Coulomb barrier and fuse together to form the deuteron, which is the lightest bound nucleus that we have. The deuteron is a neutron-proton bound state, so there also has to be a weak interaction that goes on to convert a proton to a neutron. And then deuterons can fuse with more protons to produce helium-3. Helium-3 nuclei can fuse to produce helium-4 plus 2 protons, and those two extra protons can go off and start the fusion chain over again. And every time we have a fusion reaction, we generate energy, which is how our sun is powered, or one of the main mechanisms by which our sun is powered. Now, this entire chain turns out to be very sensitive to the binding energy of the deuteron. And what I mean by that is that this chain happens often enough that the sun can continue to fuse and burn and create energy, but it's also slow enough that the entire sun doesn't just fuse all of its hydrogen at once, burn out, and then just be cold and lifeless. And of course, the slow burning property is important for life on planets because we need our sun and it needs to stick around long enough for life to evolve. So the whole picture is very sensitive to the beginning of this chain where this deuteron is formed, and the likelihood that you're going to form a deuteron depends on its binding energy, which turns out in nature to be 2.2 MeV, which when you compare to the binding energy per nucleon of all other nuclei, that number is roughly about 8 per nucleon. And so 2.2, that's for 2 nucleons. So around 1 is much smaller than 8, which is what we have for all of our other nuclei. If the deuteron were more tightly bound, then you might imagine that protons would very quickly fuse to form these very deeply bound deuterons because you release a lot of energy in the process. So it would want to very quickly go down to a lower energy state. So a question you can ask is this fine-tuning that's necessary for the slow-burning sun by chance? Is it just because the masses of the quarks and the couplings are as they are in nature, and they all conspire to produce this lightly bound deuteron? Or is it more fundamental? Is it a more robust feature of QCD where even if I dial the quark masses, I still get this lightly bound deuteron? So this is a question we would like to answer. As we change the quark mass, does the binding energy of the deuteron change rapidly, or is this lightly bound deuteron kind of a more robust feature of QCD? And of course, experimentalists can't do this because they are not allowed to dial the parameters of nature. An even better example of this fine-tuning comes in nucleosynthesis in older stars. So these are stars where most of the hydrogen has burned off and we're left with a lot of helium. So we have a lot of helium-4 nuclei. These are called alpha particles, and 2 alpha particles can fuse together to form beryllium-8. And then a third alpha particle can come along, fuse with beryllium-8, and produce carbon-12. Now, the issue with this is that beryllium-8 has an extremely short lifetime. It breaks apart almost as soon as it can be fused together. So the likelihood that a third alpha particle would collide with beryllium-8 before it disintegrates is essentially 0. However, there is a resonance, the so-called Hoyle state, that exists 0.09 MeV of an energy different from the sum of the masses of beryllium-8 and helium-4, such that when the probability for this process to occur, so beryllium-8 colliding with helium-4, is enhanced by orders of magnitude. Now, this resonance had to be at just the right energy that the beryllium-8 and the helium-4 in these stars would be colliding at in order to enhance this process, in order to produce carbon-12. And so this is kind of one of the favorite processes. It's called the triple alpha process for proponents of the anthropic principle, who say there's no way that this energy scale, which is much, much smaller, 0.09 MeV, this is very small on the scale of nuclear physics. We typically think of nuclear physics scales, well, depending on the nucleus. Well, we'll talk about that later. But certainly not 0.09 MeV. We're talking things on the order of 100 MeV or greater when we talk about nuclear physics scales. So where this resonance came from, well, people would say you need carbon-12 for life. You need people to be alive in order to investigate this theory. Therefore, the parameters of the standard model had to be such that they are in order for us to be observing this behavior. So that's kind of a sketch of the anthropic principle. But if you are not satisfied with such an explanation, you might want to look at the standard model, look at the parameters, and see what happens to these as we vary them. This is another thing we'd like to do with lattice. And then just to throw a third example at you, Big Bang nucleosynthesis. Also, after the Big Bang, we have a lot of nucleons that are around in our little universe that's expanding. And as the universe cools, the primordial abundance of protons versus neutrons is very, very key in how much this chain by which we produce nuclei after the Big Bang can occur. And so the amount of nuclear matter that we have in the universe today depends very sensitively on this transition between neutron and proton, and therefore the abundances of these two nuclei after the Big Bang. Okay, let me